You may have heard of TFM, but what is TFMi? Let's check it out. With regular TFM, you've got a lot of modes to pick from, right? So you usually need to know a little bit about the type of flaw and the orientation of it before you pick the optimum mode to try to image that flaw. Just a few degrees of tilt or a few facets may cause a planar defect to disappear on some modes. This makes TFM challenging to use for detection. It's really easy to miss something if you pick the wrong mode. TFMi is intermodal TFM. This allows us to combine the information from multiple TFM propagation modes into one more coherent image. TFMi is something that I developed in cooperation with Sonatest over the last year or two. It's now available on the Veo 3. Now, intermodal or multimode TFM is not entirely new. It has been available on some software packages in the past, but this is the first time that it's been made available on a field portable instrument. We can combine up to 4 modes at once in real time. You can do that in combination with regular phased array or regular TFM. For the purposes of this, I'm just going to use 2T, 3T, 4T, and 5T for all these demonstrations. We'll test it on some simple targets. First, I'll use this Vermon NDT 10 megahertz 64 element A12 transducer on this wedge, and we'll stand back a little bit from the targets just to pretend like we're on a real weld. Here I've got a stack of side drilled holes. On the left is TFMi and on the right is regular phased array. Those holes are really close to the surface, but at 10 megahertz, the resolution is really nice. Then on the other side of the block, there's a porosity cluster, again, just some side drilled holes. There are 5 of them, and from this side, we can see 4 of them, and you can see the comparison between TFMi and phased array. Notches and holes are nice for a demonstration, but they're not real. So we'll get a little bit closer to reality, and we'll use this machined crack. Here, I'll push the probe towards the crack, and we'll show a comparison between TFMi, 2T, 3T, 4T, and 5T regular TFM modes, as well as phased array. Now, the top of that machine notch is 15 millimeters from the bottom surface. It's 25 millimeter thick part. So my cursor here lined up at 10 millimeters down from the top lines up really well for height sizing. Now that looked really good, especially comparing the TFMi to the regular TFM modes. But how does it perform on a real weld piece? Well, in this case, we're going to use a Flawtech 1-inch sample, and it has 3 flaws. It's got a root crack, a toe crack, and a sidewall lock fusion. From the first side, using the same 2T, 3T, 4T, and 5T combination in TFMi, the root crack and the toe crack both image really well. In fact, if we zero in on that root crack in a different scan, you can see it follow the prep on the bottom, and then it moves up into that angled bevel face. And on the toe crack, it's less faceted than the root crack. Sizing is fairly simple, as the 4T signal dominates that intermodal combination and gives us a really good tip diffraction. We get about 4.6 millimeters for TFMi, which is the same as what we get for phased array. Again, no change to the setup. Looking at the lack of fusion from the opposite side, the fidelity on that is also really good. The whole point of TFMi is improved geometric fidelity. We can make a better picture of the thing we see in the weld. It's robust in that we can use the same combination of propagation modes to find a whole array of different flaw types in different parts of the weld. We cannot do that with regular TFM. It's really easy to miss things, and a better picture of the flaw makes a better report. I hope you found this video useful. If you did, please hit the like and subscribe buttons, and thanks for watching.